So I was making this into one video, but it was too long. So now it's split. We just finished talking about discrete random variables. Now we're going to talk about continuous random variables. Let's go. Okay, now we're done with discrete random variables for now. I'm going to look at continuous random variables. So while a discrete random variable had gaps, a continuous random variable will not. A discrete, you can count a discrete random variable, okay? But continuous usually involves situations where you're measuring something. So even like weight, height, length, width, area, volume, while in reality we measure these things and we can argue they're discrete, okay? I'm thinking already if some of you are saying, well, these are discrete too. We treat them as continuous, okay? Because it's too many to list. Think about it. If we're measuring the like weights of kids in a certain age range or something, because that range could be so large, we would have to count 80 pounds, 81 pounds, 82 pounds as each individual. But when we use a continuous random variable for measuring, it makes it a lot easier to digest and analyze the data. So a continuous random variable takes on a value in an interval of values. The probability that we're looking at here, this will be good, of x, or whatever x is, like weights, length, height, volume, area, that'll be described by a density curve. This should remind you of this a little bit, right? When we talked about density curves, okay? The probability of an event is the area under the density curve and above or below, meaning like to the right or to the left. Okay, I don't like the above or below. This would be to the right, and this would be to the left of the value of x that make up the event. Above meaning numerically above, higher, larger. Below meaning numerically below, less than. But when we look at the density curve, above really means we're picking a value and looking to the right. Below means we're picking a value and looking to the left. Okay, probability model of a discrete random variable x assigns a probability between 0 and 1 to each possible value of k. It's not what we're doing with a continuous random variable, though. A continuous, and I might just write Cont from now on, random variable y. So now we switched gears. We're looking at y. So let's switch to blue. That has infinitely many possible values. So all your continuous probability models assign a probability of 0 to each individual outcome. Okay, let me repeat that. All continuous probability models assign a probability of 0 to an individual outcome. Okay, only an interval of values will have a number other than 0 for probability. Okay, so take a moment, read this, and I'll pause. All right. We're going to use blue because we're talking about a continuous random variable. Highlighted some things. We have mu of 64. That's the mean. We have standard deviation of 2.7. And here's a phrase here. Normal distribution. So we have n of 64, 2.7. That's important. Okay. They're asking about these young women and their height. What's the probability the chosen women in this sample, because it's repeated very many times, is between 68 and 70. So we're looking for the probability that y is between 68 and 70. Okay? So here's what we can do. So first of all, let's draw our normal curve, which is what we're going to do. And then right here, I have 64. Okay? A little arrow that's there. And then we're looking at what are the probabilities that we're at 68 to 70. We're looking at that. Okay, so let's do this a couple ways. Let's do this kind of by hand. So first we can normalize it or standardize it here. So we have 68 minus 64 over 2.7. Remember, this comes from our y minus mu of y over standard deviation of y to get the z-score. So we're looking for the z-score. I might as well leave that up, but it's in your formula table. That equals 1.4815. And the z-score for the other end of our interval would be 70 minus 64 divided by 2.7. And that's 2.22222, whatever. Okay. Standardize it. We can look at the table, okay? Or we can go normal CDF. And we have our lower bound, 1.4815. Our upper bound at 2.222, okay? Our mean is 0, and our sigma is 1, right, for standard. Or we can do our lower bound at 68, 70, 64 for our mean, and 2.7 for standard deviation. You can do either one. This, I know this video is getting a little long, my apologies. This is the z-score, okay? And this is the raw data, not standardized by that. That's what I mean by raw data, okay? And so this is going to be about, when we're all said and done, let's switch to green here, it's about 0.0561. So what does that mean in the context of the problem? So I wrote my, oops, sorry, my chair is creaking. What we normally do for normal distribution, large capital N, parentheses, the mean, and the standard deviation. Then I'm looking for the probability that the height of this woman, or these women, is between 68 and 70 inches. I can standardize it. So the lower bound is here, 68 minus the mean, divided by standard deviation, 1.4815. Standardate the upper bound, which is 70. I get 2.22222. We already went through this. You can do normal CDF, and then you get your standardized information, lower bound, upper bound, mean, sigma, standard deviation. I said the wrong thing? I meant lower bound, upper bound. Sorry. Or you can just use the raw data, normal CDF in your calculator, and then you do the lower bound, which was 68, upper bound of 70, mean of 64, standard deviation 2.7. This equals 0.0561, about. So then in context, when considering many women, we would expect approximately 4.61% chance, I left out the word A there, that a randomly selected woman measures between 68 and 70 inches tall. So context and units. Here's our final example. I'm going to pause and fill some things out. You can do the same. Let's proceed. So I highlighted a few things. We have weights of 3-year-old females, normal distribution with a mean of 30.7 pounds, standard deviation 3.6 pounds. This is where those growth charts come from, by the way. We're going to call our weight Y. I'm going to change it, calling an audible here because we've been using Y for continuous variables. That's what we have. Find the probability random selected 3-year-old female weighs at least 30 pounds. So what do we have here? I have a normal distribution, normal of mu and standard and sigma, of 30.7, standard deviation 3.6. What is the probability that this 3-year-old's weight is going to be at least 30 pounds, so greater than 30 pounds? Okay, I'm going to standardize my statistics. I'm going to get a z-score. I'm going to take my target value, 30, subtract the mean from it, divide by 3.6. That's going to give me negative 0.1944. Sorry about that. I have my normal distribution curve, my density curve here, and I use the standard normal so you can see. I use standard normal, 0, 1. So 0 is my mean, and I have my standard deviations down here. Doesn't have to be exact. And here would be approximately the line negative 0.1944. It's not exact, doesn't have to be. And look, what I'm looking for is the shaded area. So I use the normal CDF. My lower bound is negative 0.1944. Upper bound is infinity, or you can even write 10 or 12 or whatever. I got 0, and then I got 1. Or you could use the raw data. 30 is my lower bound. My upper bound is infinity. My mean is 30.7. My standard deviation is 3.6. Both of these will yield the same numerical value, 0.5771. So, and that makes sense. I wanted to show you, this is above half. 0 is the halfway line, so if I go below it, that means my shaded area should be more than 50% of the density curve, and indeed it is. So what does this mean in context? What does all this mean if I'm just telling a parent, right? When you see those growth charts, they just don't go, your kids here. What did they explain? What does it mean? So in this context, which would not be a parent conversation, when considering many 3-year-old females, I'm only going to have one, maybe two. If I have twins, triplets, if it's super rare, there is a 51.7% chance that a randomly selected 3-year-old female weighs more than 30 pounds. In context, 3-year-old females and units, pounds. Also, you can replace more than with at least. That would be the same because that's what it's asking here. Weighs at least 30 pounds. And that is all for the lesson. I apologize for the length of the video. Probably in retrospect should have split these up into 2, maybe even 3 or 4. All right. If you need anything, you know how to get a hold of me. Good luck.